Okay, let's try again. We need to go through design principles of building a scalable network, and then look at switch and router hardware options, which in these presentations from Cisco are purely a marketing exercise, really. You get this information off their website, shouldn't need to be plugged in, of course. So, we need to look at options that provide us with the ability to have a converged network, which means we support voice, video, and data traffic. We need to be able to recognize and support critical applications across our network. So we need quality of service. We need to understand and address business needs, because depending on the requirements of the business and their focus will require different methods of handling the traffic. And to make life easier, we need to centralize administrative activities to make life more efficient for the network IT support team and to minimize disruption whenever we need to make a change. So we need to be able to build a network from being a small 1 or 2 switched type network and expand it in a controlled manner as the business expands. So to do this, we need to have an approach that is hierarchical and builds on principles of design. So we need to be able to connect to any device, anywhere, anytime, and the network needs to be secure, reliable. All right, so it doesn't matter whether we're using copper, fiber optics, wireless. We need a unified approach where everything works together seamlessly. So to do this, our design principles need to be hierarchical, as I said, and modular. We need to be able to replicate, and that's the guiding principle behind scalability. So if we have a design that's already proven itself, we can take that module and replicate it as many times as we need. We already know the equipment and how to set it all up. That will make the network resilient and flexible, as we can just add these modules as we require them. So we have 2-tier systems and 3-tier systems, in that we have core, distribution, and access layers. Now, as we're building up from a small network to a medium network, we'll quite often run a 2-tier system where it has a collapsed core, which means we have the core and distribution layer functions working together. It just means we haven't had the need to separate the core functions out by themselves yet. Or what we need to do is build to a principle, and the principle is an access layer provides access to the network. This is where the user's devices access switches, and these switches are connected to the distribution layer. The distribution layer implements quality of service, security, and routing. So this is where our policies are applied. We start aggregating large-scale wiring to limit the broadcast domains. So distribution layer switches connect both the core and access layers. So it's the middle layer. The core layer is our backbone, which connects several layers of the network together. It provides our isolation so that faults do not propagate throughout the entire network, and it provides high-speed backbone connectivity. It doesn't have any user support in it. It's all about speed and interconnecting all the elements together. So, three-tiered, generally speaking, are used by large organizations, and they use an extended star topology with generally a centralized location that everything comes back to. Whereas a two-tier model is where we don't have to have that core separated, as we don't have as many locations to centralize. So this is basically where we're spread over multiple floors within the same sort of building, so we don't have that larger distribution. All right. So in the three-tier mode, we're using access and distribution in each location, and then they all interconnect into the hub or the core for distribution throughout the entire network. Because you've got limited locations, we don't need to have those functions separated quite as much when we go to a single building location. So it's really just a decision on our part on how we manage our design architecture. And if we follow the same principles throughout our design, the natural growth of the network will force or dictate when that core functionality is segregated out and provides that service by its own. Right? So as networks grow and change, they'll go from a switched local area network that require a distribution between the switches to keep their redundancy and aggregation points flowing up. Remember, we designed this like a pyramid where the access layer is down the bottom and it's broad, and we come up to the point which is the core. So it's filtering our traffic upwards and aggregating it, and our policies need to be applied somewhere, and that's in the distribution layer. So scalability means we can grow without losing our reliability and availability of our existing network. So to do this, we need to incorporate redundancy, use multiple links. We have to have a scalable routing protocol, and we need to incorporate wireless connectivity where and as appropriate. So redundancy in a network means we have basically a fully meshed network. So we need duplicate equipment with duplicate connections. This avoids a single point of failure. Now, this is not always possible based on budgetary constraints. But basically what we want to have is an alternative path from as close to the source of our traffic all the way up. Now, this poses a problem in switched networks because of loops, and spanning tree protocol is there to limit loops. Its sole purpose is to eliminate them. So what we need to do is create a traffic pattern that we can control, and this is where per spanning tree instances of spanning tree come into play, because we can then shape traffic to make use of these redundant links so we don't overload any given uplink as we move from our access up to our distribution. And it still maintains the physical links, and we make better use of the available bandwidth. Now, what we want to do is limit the size and impact of failure domains, which means those routing loops or switching loops are contained. So these areas of failure are terminated against our distribution layer. So basically the way we do that is introduce multi-layer switching, and this becomes our gateway to our access layers and provides that inter-VLAN routing in a switched environment. Now we can do this via routers or multi-layer switches, normally with multi-layer switches. So each switch block acts independently from the others, and that way we can eliminate losing our entire single point of access. Now, for most people, we don't have multiple network cards in our host devices active. And in a fully redundant network, we would have two cables coming down to each host machine, and we would then be able to access the network via our two access layer switches. So the trade-off is we have devices connecting to a single access switch. So that becomes our single point of failure. But moving up, because we dual home each of those access layer switches to different distribution layer switches, that alleviates single points of failure after that. So if a link fails going up to the distribution, we have an alternative path and can maintain connectivity. It's only if we totally lose the access layer switch that we are in problem. So to increase our available bandwidth as our network expands, we start combining links together in ether channels. So this link aggregation allows us to increase the bandwidth between devices without creating loops, because ether channels combine and act as a single channel. So we can have multiple physical links combined into one virtual link, and that way we maintain a single link between our switches, so we don't have loop issues as far as spanning tree is concerned, and we double our bandwidth. We provide redundancy in that we've got multiple physical links that can still maintain connections if even one link fails. We provide load balancing between those links, so we don't overload any one given link. We load balance between all of the physical links in the channel. And this provides us with a very robust redundancy between our switches. One of the ways we can expand our switched fabric is by putting wireless access points into our network. This increases the catchment of any individual switch to include all the devices that connect via the wireless access point. Now, we need to consider how we're going to connect the wireless in. So we need to look at our coverage requirements, our interference patterns, security considerations, all of which was covered back in the wireless chapters back in SRE. So that entire course, SWRE, now that course had chapter 12 and 13 dedicated to wireless. So if you need to do any refreshing on wireless, go back and have a quick reread of those two chapters. Next, we need to tune our routing protocols. Now, the one that we've concentrated on so far was OSPF. Now, this is a protocol that is designed with scalability in mind. We can limit the impact of changes in our design by segregating into areas. So each area gets summarized, so their link updates only travel within the devices in their own area, and they have minimal to no effect outside of the area, because the areas summarize the routes that are available inside the area at the area border router. This allows us to scale networks, and all what we've got to do is add another area that connects into 0, and we can continue to scale our network as we grow. Each router will synchronize their appropriate databases and provide the best pathing, and they'll self-propagate these new links throughout the entire network. So it's basically infinitely scalable and will provide the best path available within minutes of a new section coming online. Now we get into what I consider the marketing pages. There are some design considerations as we move through these pages, but most of it's just sale propaganda. So when we look and evaluate switching solutions, we need to take into consideration the switching platforms, because depending on the platform, we get different feature sets. We need to consider what form factors we want to use, whether they're fixed or modular, what basically meets our requirements, and are we able to scale the solution as required into the future. Now, both switches and routers play critical roles inside our network communications architecture. So you do need to understand how these devices work and interact with each other and their limitations. Now, the limitations are imposed by the platforms themselves and their form factors. Okay, so if you buy a switch that has only got 24 ports and it's a fixed form factor, then you can't expand that device by adding more switch ports. You have to buy another switch. Whereas if it's a modular one, well, you can buy another module and expand it, for example. Now, depending on your device, depends on how scalable that particular device is in itself, or in combinations with stacking. Now, stacking of switches has been around for a very long time. What's changing is the ability to stack switches virtually. In other words, software-defined networking. So Cisco Meraki solutions are cloud-managed access switches that allow us to virtually stack switches together, and this allows us to monitor and configure up to thousands of switch ports over a web-based interface with very little interaction from our IT support staff. Whereas if we go back to our more traditional modular devices as seen with the Nexus platforms, they promote large scalability, operational continuity, and flexibility by being modular. So if we need to expand them, we go out and buy a module for that platform, and it increases the features available to us. And most of these modules are hop swappable. In other words, we can plug them in and take them out without shutting down the device. This includes power sources as well as individual modules. So it's quite a different way of approaching it. So when you do your research for your solutions as a network designer, you need to look at what features are available on any given platform. And these include unified services, virtualization, security, and management features. Whether or not you can segregate this by virtualization in the device. So in other words, can you if you're working for a service provider, you don't want to buy new hardware every time you plug in a new client. You want to be able to use your existing hardware to support multiple clients. So this is secure multi-tenant services. You need to be able to segregate your hardware in such a way that your clients cannot see your equipment or the services that you are offering to other clients. So form factors are what determine what options physically we can have. So they can be fixed configuration, modular configuration, stackable, non-stackable solutions. So you need to read the specifications, all right, and make appropriate choices. because if you make the wrong choice at the beginning, it can be costly to scale. Okay, so with the ability to provide stackable switches, or what you've got to do if you need to increase your port count, but not necessarily want to change your policies and duplicate it multiple times, you can stack multiple switches and interconnect them with stackable cables, which are these big thick cables hanging off the back. And what these do is they stack and connect to the switch above, and then the top one loops down and connects to the bottom. So they form a total loop within themselves, and this is a backbone between the switches. And what happens is one of those switches becomes the master switch. So it's in control of all the other switches. And what they do is they use that backbone to provide connectivity between any of the switch ports on any of the forms. So the physical switches act as one large virtual switch. So instead of just having a 28 port, 96 port switch, we have multiple switches interconnected, and they can work as a single, 180, 190 switch port. Depending on the model, depends on how many can go into a stack. So you can have 8 48 port switches working as a single switch. And if you have one of those physical switches fail, then all the others just reverse their traffic flow through the backbone links to be able to access all the other ports except for the ports on the fail. So it's like losing a module in a modular switch. You just replace that faulty switch, repatch it in, and the master of the stack will push out the appropriate operating system to the new member. It will then push out the configuration of the ports that are assigned to the various VLANs and bring it back in line without any further interaction with us humans. So stacking solutions are very flexible and very powerful. Port density comes into play a lot in our solutions because your typical 2800 series device comes in standard 12, 24, or 48 port configurations. Whereas if you go into a modular switches, we can increase that to hundreds of ports, such as the Catalyst 9400 switch, which supports 384 switch ports. So as you can see, we need to take our requirements and find the platform that allows us to provide that support. Now, one of the things you need to ensure you look at when you're making these choices is look at the backplane available on these modular switches, because the backplane will determine how much information flow can be supported between the modules. So the overall forwarding rates play a big decision in our selection process. So this is the total rate of how much data a switch can process per second across all of their ports. If the rate's too low, we cannot maintain full wire speed communication, which is the benefit of having switches. Okay, so as we aggregate up, remember our speeds now are 100 megabits, 1 gigabit, 10 gigabits, or 100 gigabits, and that will change as we move forward in time, as technology improves. So we need to maintain full wire speed and not be limited by our links. So when we're aggregating, we're taking, say, 24 1 gigabit ports, and if we've only got 10 gig uplink, do you think that might be a problem? If we're trying to maintain 24 gigabytes of speed from all our hosts up a 1 gigabit or a 10 gigabit uplink. All right? Yes, all right, not everybody's going to be broadcasting at the same full maximum speed all the time, but we've got to look at our traffic patterns and provide solutions, especially for businesses that have high data requirements. Okay, I've done research labs where they're using MRIs all the time, and they're dealing with 10 gigabyte or larger single files in their imaging and research. So those solutions required multiple ports with multiple backup links and very high switch capability. Now, when we're supporting voice applications and other things such as CCTV, we need to know whether or not we're providing power over our Ethernet connections. Now, this is becoming more and more the preferred solution, and we need to look at how many ports we can have active. So in other words, how many ports on the switch can provide power over Ethernet. And then we've got to look at how much of the overall power we can supply, because each device requires a different level of power, and we've got to cater for the individual needs. And then remember, if we add all those ports up, the total power requirements have to be supported by the device. So we can't just whack a switch in and say it's got power over Ethernet and forget about it. We actually have to look at the devices we want to connect to it, take their average and burst power requirements into consideration, and make sure the switches can support the total. Now, moving on to multi-layer switching. We need to know when to keep it at layer 2 forwarding and when to provide routing protocols to forward our packets. Because at some point, it becomes more profitable for us to be routing packets rather than switching frames. So this is where we need to look at our application-specific requirements. ASICs in our switches are our dedicated inspection tool that makes our forwarding decision possible, and it works with our forwarding infrastructure within the switch to make the decision. So overall, what we need to balance is cost. Now, cost is going to be our number one deciding factor on designs, because we never have enough money to build a perfect network. So what we have to do is come up with a solution that provides the best performance for the budget we're given. That's always going to be our number one constraint. Next, we need to make sure we have correct port densities where we need them. We need to confirm that we have the appropriate power availability where we need it. We need to provide reliable, continuous access to our users. We need to make sure that we're supporting the end users as far as speed is concerned. We need to look for and mitigate any congestion bottlenecks within our design. And the typical areas are where we have servers and aggregation points within our network. That's generally where congestion will occur. We know this because that's the way we've designed the network. Now, always take into mind that businesses need to grow. Their basic business mantra is that they are always looking to increase their market share, which means they always need to grow their business. So when you're doing a design, you'll generally have to look at their projected growth, because remember, they're going to say this network needs to survive 5 or 7 years or something like that. So you need to look at their projected growth and then line up how they're going to support that growth over the time. You may not need to build it right now, but you need to have a solution so that you can plug in more equipment and provide that solution as it comes about. And address the routing requirements. Again, we're going to look at some marketing slides because we're just looking at specific hardware. And all what you need to take out of this is knowing the general rules of how to do your research when you're doing your design. So as we know, routers route packets to their destination network. So we need to be able to provide our routing solutions with redundant links or alternative paths so that we can still maintain connectivity if one of our devices falls over. So what do routers give us that switches don't? Well, they provide broadcast containment. Remember, broadcasts will propagate through layer 2. They will only stop at a layer 3 device. We use these devices to interconnect large, geographically separate locations. We group users logically by their application or department within the company so they can access required resources. And these devices provide us with enhanced security by filtering traffic. So ACLs, access control lists, provide that filtering, and those filters are what firewalls are based on. So when we look at a branch router, we don't need all the bells and whistles as a large headquarters router. All right. So we need to provide a device that will be optimized for the services required at that location. Now, it's always good if we can use the newer integrated service routers that cater for this new converged solution that everybody's moved towards. The older ones were not built with that in mind, so be aware of that. So what do we mean by an integrated service router? This is the one that allows us to have multiple features and cater for various applications. So our voice, our video, our data, and remote access, firewalls. We need to have many features within our devices. It's generally speaking on a branch. They're our point that everything needs to be applied at. So when we're looking at edge routers, which a lot of branch routers can be considered at, we need fairly high performance, highly secure and reliable services that are used to unify the entire campus. And then you come up through the aggregation points, such as data centers and our distribution areas, and we need to aggregate all those services through these high volume locations. So we need aggregation service routers which are built for the volumes of traffic that they will see. So compared to branch routers, these ones are designed to aggregate hundreds of branches together. So the volume of traffic these devices are designed to handle are much larger, and just about all of them come in modular form factors. Okay, because we need to expand them to cater for our solutions. Now, when we go up to our lovely service providers, they're handling even more aggregation points than the ASRs. These need to be subscriber-aware service, provide end-to-end scalable solutions. So these dedicated devices are known as network convergence systems. They provide super fast, super scalable solutions, and they cost a fortune. All right, so what about the other end? All right, normally when we're looking at things, we're talking commercial solutions. All the examples we've gone through are, office spaces. Guess what? There's a whole other section called industry. Now these are, in chemical plants, out in the field, so they need to be rugged, self-contained boxes because they're going to be exposed to harsher environments. So these require a dedicated set of devices specifically designed to be used in these environments, such as mining, out in the environment, in little boxes somewhere. So the Cisco 1100 series of industrial integrated service routers provide solutions for this environment. They generally don't have as the same port densities as you would get in an office environment because they're not supporting as many devices in the field what we're doing is providing connectivity to a smaller catchment zone, because we've got to be more robust, and having more of these interconnected with each other. So we can have very small form factors like we would see in our domestic environment, but these combine a lot of different things. So generally speaking, they're fanless and don't generate as much heat as our commercial cousins. So they will provide WAN, switching, security, various advanced feature sets depending on the options required, but they're designed to cater for small to medium businesses. Remember, our ASRs are there for our large distribution activities and moving into our core requirements. So that's our ASR devices. And then our converged systems, so our ISP type or very large enterprise solutions. What's the difference between an ISP and a large enterprise company? One servicing their own internal clients and the other one is servicing external clients. Still require the same solution. All right, so horses for courses, as the old saying goes. So we need to select the appropriate routers that is designed to cater for the volume and type of traffic. And that's what all of these slides are there to remind you of. All right, so the packet tracer activity for this one is for you to look at the differences and compare a few different things and see that they basically work the same, even though they're in a different form. A lot of the functionality is the same. So to recap what we just went through, we looked at the basic design principles of hierarchical design using a 3-tier layer model that combines access, distribution, and core as functions. Okay, and depending on the size of your network, you may need to do a flattened model which combines access and then core and distribution cannot be distinguished as they are squashed together. What you need to remember is the basic design principles of providing redundancy, the ability to aggregate physical links together into virtual links, providing enhanced bandwidth options without compromising the integrity of spanning tree, and keeping our switching fabric loop free. This will provide us with scalable solutions, as we can always bundle links together as we need to scale and provide more bandwidth, as long as we have the port capacity on the devices that we're doing this with. And we need to provide routing protocols that support the scale increases of the network as the business grows. And one of the ways we looked at was using a scalable routing protocol such as OSPF that supports multiple areas. So what we can do is replicate a module, plug it in as a new area, and we support scalable solutions with minimal impact on the rest of the network. So there's very little disruptions. We looked on the fact that we can quickly add wireless connectivity to provide expansions where appropriate. It supports mobility as well as expansion of total number of users. We looked at the ability to stack devices or have modular form factors that we can swap modules in to provide scalability. Excuse me. And one of the solutions was software-based virtual networking solutions that we could provide segregation and stackability of switches in different locations to behave as a single device, even if they're not in the same location. We can then look at the available devices, both in switched and router form factors, and their features to select the most appropriate solution to cater for our requirements that the network needs to provide. Routers provide better redundant pathing solutions, general rule of thumb, because they are not critical of having loops as switches are. So we looked at the various switch hardware solutions, and then we moved on to looking at the various switch router solutions, and these routers were categorized into branch, network edge, service provider, and industrial solutions to provide an appropriate degree of A, the form factors, and B, the capabilities. The main one being the overall bandwidth that they can support. So the amount of traffic they can support. A branch cannot handle the traffic that a service provider will need, for example. It just can't handle the throughput. So you need to design based on your projected growth and your overall bandwidth requirements or throughput. And that brings us to the end of this morning's presentation. As you saw, a lot of it was marketing PR in that, selecting the appropriate Cisco device for its capabilities. Now, take from that the principles that they're talking about. Get rid of the Cisco brand. All right. You need to evaluate the devices, regardless of the brand that's on the outside of the case. You need to evaluate the device on its capabilities and the appropriate services for your business requirements. You don't just purchase equipment based on the brand on the outside of it. Okay? You choose the most appropriate device for the system's requirements. And then you work out whether you can actually afford it. As I said, the number one design problem we face is budget. All right, we need to make sure we can get the best network design we can get with the budget we're given. This has come to the forefront because the main campus I work at here in Australia is the Bendigo campus, and we're in the middle of tearing down buildings and rebuilding the campus. All right, so we're doing a major campus refresh, and the IT project manager has decided to involve the IT teaching department in this process. So did we have input into the design and that? No, we didn't. All right, we didn't have input into the tendering or anything like that. But what we are giving our input in is to enhance our teaching capabilities, and we got to propose our preferred solutions for increasing our scope of potential teaching. And B, we were able to negotiate that our students could participate as work experience in the rollout of our network. So 2 or 3 of our students are going to be actively building the new campus network in conjunction with the contractor that is engaged to do this. So that provides our students with a wide range of exposure, and it also exposes the students to a new firm where they might potentially get work in the future. So it's a win-win situation. So going through this and exposing the principles of design and then seeing it play out, and having discussions behind the scenes of how much we need to squeeze within those budgets and the negotiations about what we can get for the money highlights that ever-present cost factor. So I'll let you go work on reading chapter 11 and working through the couple of activities that are attached therein. And this afternoon's presentation will be on module 12, which will be going back over all the troubleshooting type activities that we've covered over the previous chapters in all the courses in one location. So as we've gone through the various chapters on configuration of devices and features, we talked about individual potential problems and troubleshooting encountered in that area. This chapter will combine it all and talk about individual elements again and highlighting the overall requirements of having a rounded technique to troubleshooting and keeping appropriate documentation and things like that. So that'll be this afternoon, and I'll check back with you around about the 11, 11:15 mark. See how you're all going. Until then, I'm available via WeChat and email, and I'll catch you at 11. Bye for me.